Thank you, Karen. It's nice to be here. Just so that you know where I'm coming from, I'm a fully paid up environmental economist with an amateur interest in philosophy. So this is a fun workshop for me. And I'm going to be working within a standard welfare economics frame. So a lot of the things discussed this morning are going to be sort of well outside the purview of what I'm going to be talking about strictly. But what I'm going to try to show you is that I can sort of turn cost-benefit analysis and its standard methods and principles a little bit on its head without moving away from the basic fundamentals. But I can do that in such a way as to render the choice of discount rate and utility function supposedly critical choices to make in cost-benefit analysis of climate change. I'm going to show you that they don't matter. Moreover, I'm going to give a precise sense, I'm going to give a precise meaning to the claim that you would have to be almost, quote, almost crazy not to want to cut greenhouse gas emissions by a very large amount. I'm going to do that within a standard welfare economics frame, so I'm going to define craziness in terms of time and risk preferences. So this is joint work with Anka Matai, who was a visiting PhD student of mine a few years ago and is now in Seville at the Joint Research Centre of the European Commission. So our starting point for this work was to note that many investment problems involve both long time horizons and risky returns, so uncertain payoffs over a very long period of time. And, you know, if you were going to write a book on investments that paid off over a long time with uncertain payoffs, climate change would be a great motivating example. So, assumptions about time preferences, I mean basically discounting, and risk preferences, I mean how you aggregate the value of different states of the world in your model are going to be important. And the trouble is that these are, you know, these assumptions are hard to make, and they're famously debated, particularly in the context of public investment, where, in addition to the issue of working out what individuals' time and risk preferences are, you have this issue of how do you aggregate them to construct the preferences of a social planner in the context of CBA. And we're just going to go right out and say something which probably has a lot of philosophical meaning, but for economists are sort of reasonably happy to go along with this, and I suggest that if we want to discuss this, we do it at the end of my talk. But we're just going to go ahead and say that economists are never going to agree on the discount rate, the discount function, or the utility function. There's always going to be a debate between Stern-type people who believe that we shouldn't weight future generations differently to today, and Bill Nordhaus-like people who do. And they're just going to keep arguing about it, A, because there's some normative content, and B, because they have no obvious qualifications to discuss normative issues being economists. And that, from the point of view of specifying the preferences of a social planner for cost-benefit analysis, that is the same thing as saying we have incomplete information about what the discount and utility functions should be. But we wonder whether this matters, the fact that we can't agree on these things. I would say that conventional wisdom is that it does matter, that the choice of a climate policy, meaning how much to cut greenhouse gas emissions globally, depends critically on things like discounting. And we're going to ask, does it really? Or could we find a so-called space for agreement? In other words, if we brought together a group of people who had differing time and risk preferences, a Nordhaus, a Stern, and some people in between, could they nonetheless agree on which of a set of climate policies to choose? Which, from the point of view of decision theory and choice theory, is basically saying, can we construct a partial ordering of climate policies based only on partially specifying time and risk preferences? And you know, those of you who've worked a bit in economics or decision theory will perhaps realise that one or two of the tools that we might need to do this actually already exist. In particular, there is the theory of stochastic dominance, which is used to choose between risky investments. It's a sort of fundament of the theory of choice under uncertainty in economics. And there is a corresponding theory of time dominance, which is it just takes stochastic dominance and recasts it in an intertemporal domain as the choice between two investments which pay out a certain cash flow over time. But the problem is that for the purposes of climate change and other investments which are both intertemporal and risky, stochastic dominance is basically an atemporal framework. It has nothing to say on discounting. Okay? It just says that you make choices between investments in terms of how much they pay out in the last period that you're considering, and you're not interested in how much they pay out in between. Well, that clearly doesn't allow you to prefer to have payoffs earlier rather than later, or vice versa. Time dominance was a theory that was developed when thinking about capital budgeting problems in economics. Two investments, they both pay out a stream of money for sure over a fixed period of time. Now, you could use that to evaluate expected cash flows, but you would have to make some quite strong assumptions to do that, which don't hold in the context of climate change. So one of the things we had to do in this project was to unify stochastic and time dominance and to create a theory called time stochastic dominance. Not very imaginative, but the basic idea is that you're looking at dominance relations in two dimensions, time and risk. Okay? Just to elaborate a bit more on the theory, and I apologise for this, there is a lot of maths in this paper. I've tried to get rid of as much as possible. I realise from this morning that I probably haven't got rid of enough, but I'll try to, wherever I put up some equations, I'll try to explain them. So, I mean, this is basically just to say that the standard purpose of cost-benefit analysis or investment appraisal in economics is to work out the net present value of an investment X, given that your particular assumptions about your discount function V and your utility function U. Right? Your discount function V is just a function which gives you the schedule for your discount rate. Okay? And normally we pays our money and take our choices on V and U, and then we just go ahead and crunch net present value. And we should prefer the policy that delivers the highest. We would like to do this, but we would prefer not to completely specify these two functions. We would like to acknowledge that people disagree on exactly how they should be specified, and we would like to know whether it matters that people disagree. So a space for agreement formally then is a combination of classes of discount and utility functions for which one policy dominates another. So anyone whose preferences are representable by discount and utility functions in these classes would prefer one investment over another. And so the question is, how big are these classes? So the broadest class of utility functions we can consider is the ones that are non-decreasing. This simply says that a person never prefers less of good X to more of it. Generally prefers more to less, or at least is indifferent. And no economist would disagree with that, especially when the concept of the good X is some generalised income. The second class of utility functions we consider narrows this to the class of functions which is increasing but at a decreasing rate. This captures the idea of diminishing marginal utility. You prefer, the more you have of good X, the less you want more of it. It implies risk aversion and inequality aversion in the context of social choice. In terms of discounting functions, the most general that we consider is the one where the discount function is decreasing. That means that the future is valued less than the present. But it may be only valued very slightly less than the present, or it can be valued a lot less than the present. So this is capable of capturing a range of views between Stern and Nordhaus and beyond. And that we don't need to worry about. So sort of an intuition for the theory. So how many of you are familiar with stochastic dominance as an idea? So really not very many of you, which is a bit of a problem for this paper, but not too. I mean, the basic idea is that I need a discount on the time I've got available on my talk. I'm now doing.
Take a bit more time.
Okay, because I'm doing level 2 microeconomics as well as my talk. So the simplest case is first order stochastic dominance. So what we're going to do is we're going to compare, so this would be, we're going to compare two risky investments in terms of their cumulative distribution, cumulative probability distributions. So we've got cumulative probability running up one axis and outcomes or payoffs on the other axis. And the idea, let me put down two alternative payoff distributions for you. Let's say that this is a distribution F. Yeah, that makes sense given my. And this is distribution G. And this is approximately a probability of 1. This is a probability of 0. The idea of stochastic dominance is to say that anyone who has a non-decreasing utility function, so anyone who prefers more of the good to less of the good, is going to prefer investment F. Because if you think about the fact that it is its cumulative density function is always below that one of G, that means that it will always pay out for any given it will always pay out a higher amount at a given probability, or at a given probability it'll always give you a chance of paying out more. It's always going to be a better investment. So we say that at first order stochastic dominates G. Problem with first order stochastic dominance is that in most real life investment situations you won't find one distribution which is always below another. They're going to cross. But it turns out that if you integrate further, you can get to a situation where they may not cross, and you can link that to utility functions, which is probably about all I can say about this, except to say that this is the logic for dominance in any dimension. You're looking, if you think about an investment in terms of the distribution, you're looking for an investment that always lies above or below another distribution. In stochastic dominance, these are two-dimensional distributions. They're in terms of probability and payoff. In time dominance, they're two-dimensional distributions, but instead of probability and payoff, it's payoff and time. And what we have in our theory is simply we take it to 3 dimensions. We have probabilities, payoffs, and time. So instead of trying to think about whether one distribution sits above another, we look at whether one surface sits above another. Literally like thinking about that. Put two 3-dimensional surfaces, one on top of the other. Does one always sit above or below another? That's what this approach does. And then what we do in the paper is prove that if one distribution sits always below another, then that implies that its net present value is higher than the other, and the opposite implication also holds. So if and only if distribution F lies everywhere below distribution G, then we can say that we would prefer distribution F to G. Now, the trouble is that dominance can be very hard to demonstrate, so that this might appeal to you. This is the classic example which confounds dominance as an approach, and probably explains why, despite the fact you can find it in every economics textbook on risk, very few people actually use it for any practical purposes. So this is the classic example. So take two investments. Investment F will pay you 50 cents with a probability of 1% and $1 million with a probability of 99%. And investment G will pay you out $1 for sure. Right? Now, virtually everyone would agree that we should prefer investment G. So, however, you
Even we noticed this.
you got my deliberate mistake. So, most everyone would agree that we should choose investment F, distribution F in this setting. The trouble is, it turns out that investment F cannot be said to stochastic dominate investment G, not to a first order, not to a second order, not to a third order, and so on. And the reason for that is that the distributions, investment F always sits above investment G at the bottom end of the consequence space. And now integrating it repeatedly won't get rid of this bit, because it always comes at the bottom end of the consequence space. And that's a problem. And that has led to some clever folks in the management science and operations research literature proposing the idea of almost stochastic dominance. Now, it sounds like a cop-out, but it's actually really clever. Now, the basic intuition is measure the ratio of the area between the distributions where there is a violation of dominance at a particular order, in this case first order, the ratio of A1, that area, to the sum of all the area enclosed between the distributions, A1 and A2, right? And that will give you a number between 0 and 1/2. Okay? It can't go more than 1/2 because then that would just flip the problem over. Okay? It'll give you a number between 0 and 1/2. Now you might say, okay, fine, the violation is 0.001. So what? That's meaningless. But what these clever guys did is they actually showed that that could be related in a precise way to the properties of a person's utility function. In particular, they showed that the closer the violation is to 0, the fewer utility functions in the class of non-decreasing utility functions, U1, you would have to throw out in order that everyone agrees on the investment to choose. The closer it is to 1/2, the more you have to throw out. When you get to 1/2, the only utility function you're allowed to have is a linear one, where utility just goes up in linear proportion to income. Okay? We take that general notion of almost stochastic dominance and we develop it in 3 dimensions. So we develop the idea of almost times stochastic dominance. So this is what I've just said. Okay? And because we can relate the ratio of the volumes of the areas between the distributions to utility and discount functions in a precise way, we have a definition of craziness that I mentioned at the beginning of my talk. We're going to say that we're going to say that if the violation is close to 0, then you would have to have extreme preferences not to belong to this group of people who agree on the policy to be chosen. If the violation is close to 1/2, we're going to say that actually you've had, if you take the 7 billion people on Earth, you've had to get rid of 6.99 billion people. And that means that you've not only got rid of people with extreme preferences, you've got rid of almost everyone else as well. So we're going to become interested in this number if we can't prove strict dominance. So that's the theory, and then we basically take this theory to climate change. So our investment setting or choice setting is a range of characteristic paths for global greenhouse gas emissions. These paths are defined in terms of the atmospheric concentration of greenhouse gases that you have to stay under, which is a way in which policy discussions are often carried out in this area. We use an integrated assessment model to produce our data. Now, Bob has had the opportunity to influence your thinking on IAMs already once. Let me say that you could generate the data in other ways. However, we use an IAM as I am not such a I'm not such an IAM skeptic, though I agree that they have problems. That next bit doesn't need to trouble you, and that is the basic conclusion of the paper. So, yeah, so we take an IAM and we basically treat a series of important parameters as being random variables, and we sample them from probability distributions. And when we do so, we are clearly in some indeterminate world between objective and subjective probability, just to be clear on that. There are some of these things where the distribution you put in could only be described as being some kind of expert subjective PDF. There are others where the quality of the data is such that it might get closer to what you would describe as an objective PDF, although to be honest, I'm probably with, I guess, people like Savage and thinking that there's, you know, an objective PDF is probably generally an unobtainable entity. These are the policies that we look at. These are paths this is the rate at which you cut greenhouse gas emissions, ranging from nothing to 100%. This is time. This is business as usual according to the Dietz model, and these policies correspond with putting a successively tighter limit on greenhouse gas emissions. We then generate lots of charts, which I hope you will agree are pretty. Where we actually, as I described at the beginning of the paper, we lay these surfaces on the top of each other and we look at whether one surface is always below the other. And the clue here is if it's red, that condition is not met. And if it's green, the condition is met. Okay? So this is comparing the most stringent climate policy we have, which is to limit atmospheric greenhouse gases to 450 parts per million. The current atmospheric concentration of actually this is CO2 only at 450, and the current atmospheric concentration of CO2 is 400. So we don't find first order time stochastic dominance here, as you can infer from the existence of this red area. We then ask whether it exists for more or less stringent climate policies, and we find that the red area goes away, but it doesn't go away completely. So we cannot find first order time stochastic dominance of any activist climate policy over business as usual. But that shouldn't greatly surprise us because of the simple counterexample I gave you earlier. So we try it we take a higher order of stochastic dominance and we try that. That doesn't work either for exactly the reason that I described earlier. And you look, the violation is at the bottom end of the consequence space. So going to a higher order of integration isn't going to make it go away. Then we try to measure the size of this violation. And remember, we're looking for a number which is close to 0, right? And far away from a half. Ignore this column, just look at these numbers. So this table captures comparisons of activist climate policies against business as usual. So this is a series of pairwise comparisons of, say, a 450 policy against business as usual. If I get a number, ignore this column again, if I get a number close to 0, then it says that I've had to throw out very few preferences in order to form my space for agreement. Okay? And these numbers are very, very small, right? And this is for the class of people, this is for all people who have a non-decreasing utility function and a decreasing discount function. Makes no further assumptions about these folks' time and risk preferences whatsoever, except saying that they prefer more of a good to less of a good, and that they prefer a good today than a good tomorrow, with the degree of time preference, any positive degree of time preference, from tiny to enormous. And we find that we only have to throw out the most extreme utility and discount functions in that class in order to establish dominance, which is basically the numerical and conceptual content behind our claim that you have to have extreme preferences not to prefer any of these policies to business as usual. We then compare these policies to each other. Okay? The relevant thing you want to be looking at is the gamma 1 column. So how to read this? So if I compare a 450 policy with a 650 policy, remember these are atmospheric concentrations of greenhouse gases, this very small number says that almost everyone would prefer 450 over 650. Okay? So again, now comparing activist climate policies with each other, we find incredibly small violations. So that's further evidence to suggest that we only have to exclude people with extreme time and risk preferences in order to generate a space for agreement about how rapidly to cut greenhouse gas emissions. So I'll just wrap up now because I've hit you with quite a lot of stuff. So the first thing we did with this paper was propose a new way of doing cost-benefit analysis, essentially, which does not require complete specification of the discount function and the utility function, only partial specification of those. And we think that this would be useful for some instances of public sector decision making, let's call it that, such as how much to cut greenhouse gas emissions. That required bringing together stochastic dominance and time dominance, two frameworks previously proposed which partially addressed our problem but not completely. We applied the framework to climate change. We didn't find strict time stochastic dominance. We could never find that one surface always lay above another. But when we loosened it slightly to think of this idea of almost dominance in our three-dimensional setup, we found very small violations of strict dominance. And that gives, and since you can give those violations a precise interpretation in terms of utility and discount functions, and admittedly I wasn't able to go into the exact details of what that interpretation is, we used this result to argue that only those with extreme time and risk preferences would prefer weaker to tougher emissions targets in our set of choices.